Hello again. So today I am going to be covering HAL board, which stands for Horn and Lights, that I helped manage and design for this last fall and spring semester of fall 2021 and then spring of 2022 for the HAL board and the solar car. So this is also another application board, and this kind of goes in tandem with button board. So as I was developing button board last year, another member of the electrical team, Thomas Gall, was working on the first revision of HAL. So a lot of the general circuit and logic stays the same, but when I worked on the board and managed it, basically what we did is we increased the amount of current that could go through the MOSFETs so that the lights can draw on more current and they won't get damaged. We saw an issue with that. And we also changed the board to a 4-layer board just so the different signals could be managed easier. And there's just a couple things. So I'll just kind of walk through different parts of the board and then maybe things that I changed and maybe why it's needed or why we did it. So similar to button board, the reason that we actually have the horn and lights board is to take the signals that are read from the buttons on button board and output them to turn on lights on the car for different states. Examples of this are pretty obvious. Something like the turn signals where you have to turn right or left. There are front and rear turn signals on the solar car based on regulations. They have to be front facing and on the back of the car and on the sides based on certain angles of when you're viewing it at, and they do test us on this at scrutineering. One thing that's kind of interesting is I actually was the driver during scrutineering for this, so I got to see the process of them turning on the different horn and light buttons and signals and seeing how these two boards that I worked on actually were verified by a scrutineer race. So up above here, this power circuit is the exact same circuit as before. Nothing changed from the previous rev, and this is the exact same thing as in the button board video. So we try to standardize our circuits so that it's easier for different electrical members to understand them and to implement. If you want to learn more about this, go watch the start of my button board video. But to generalize it, it takes 12-volt main in from our battery pack generated through power board, and then it turns it into a 5-volt signal that is used by the rest of the board. The other stuff on this page has our compute module pins, which basically take the generate the control signals from our microprocessor. So these control lines basically are what we name are what goes to a MOSFET, and it buffers for a 12-volt output that can drive LEDs. And so there's also a front and rear selector, which we just use a switch that switches between 5 volts and ground so that you can tell whether the horn and lights system is on the front or the rear of the car. And this is to help identify with software to know which board it's talking to. The CAN lines are very similar. So two things that are different based on the other rev of the board is you can see here that we added two 10 picofarad capacitors between CAN high and M ground and then CAN low and M ground. This tiny amount of capacitance is just to help filter noise on our CAN lines, which that noise could affect our software and make it so you can't send or receive packets properly through the bus. So that's kind of why we have that. It is on the newest version of button board. It wasn't on the one that I showed earlier because we did not implement this until fall of 2021. So as I left button board and started managing this board, we decided to add that. And so another thing we did that is not used on HAL is there is a DNI resistor that's 120 ohms. So this is what we'd call a terminating resistor for our CAN line. Each CAN line needs to have two terminating resistors, which are 120 ohms each. When there's two of them in parallel between the line, you should measure 60 ohms across the CAN network. If you measure it and it's not 60 ohms, you can tell that you don't have a terminating resistor. And if you don't have the terminating resistor, because of how CAN works, you will not be able to send or receive software packets. And then if that doesn't happen, then you have an issue of you can't send a packet from button board to HAL and say, hey, we just got a signal saying we should turn the right turn signals on. Can you do that? So if that's not on, it's an issue. We don't use the terminating resistor on HAL. This is something we used last year, and we just left it on just in case we wanted to use it again, just so we could have the pads on there. So another thing to make a note of is there's a note on here where it says 12 volt crit is on rear HAL and 12 volt main is on front HAL. This is a little different than how we implemented it on race this year. So what we did on race is, since we have a front and a rear HAL, there is a regulation talking about a white flashing LED that's we call Bps Strobe. So whenever there is a battery protection system fault saying that maybe one of our battery modules is over voltage, under voltage, or over temperature from outputting current too high, or maybe there's an issue with our batteries, this BPS strobe will flicker. And so what's interesting, if you think about it from what I said in my last video, is our BPS system, we use an auxiliary battery pack before pulling power from our main battery pack, which is over 1,000 lithium ion batteries. So if you're using that auxiliary pack on 12 volt crit to monitor the batteries and you see, hey, there's an issue, you also need to have one separate version of HAL that only powers BPS strobe, because we don't want to have all our lights fully on 12 volt crit because we don't want to draw that much current from it, and we also aren't able to drive yet because the motors and everything are also on our main battery pack, and then stuff is run on 12 volt main with that. So there are three versions of HAL. There's one in the front that's powered on 12 volt main that powers the front lights and the horn. There is one in the back that powers all rear lights, so like the brake lights and the turn signals in the back. So brake lights are red, turn signals are orange or amber. And then there's a third HAL, the second one in the back, that's powered on 12 volt crit that runs BPS strobe. So to kind of cover, there's kind of two main chunks of circuits here, and they all repeat, so I'll just kind of go through one of them. So this page shows the front output. So you can see that there's two connectors here, J2 and J3. So there's a couple things going on here. So this is the output. So we have the designators here listed as headlight, turn signal L, but then we also have those control lines like we saw here. So maybe to make it easier, let's go to that MOSFET buffer first. So this page is called control signals. Here you can see we have our slide switch to detect between 5 volts and M ground to say, hey, are you on the front or the rear? And we'll just say the front is 5 volts and switch it up and down as you need. So the headlight control is just a basic MOSFET buffer that includes a NMOS and then a PMOSFET. So what this does is pretty much whenever this isn't powered, this NMOS, whenever this pin is left floating, will be grounded through this 1 meg ohm resistor. Whenever headlight control turns to 5 volts and it's outputted high, so the control line from the microcontroller saying, hey, we want to turn this light on, we would say this piece at this pin 1 node of Q6 goes to 5 volts, and then since it's an NMOS, since the VGS difference between pins 1 and 2 are greater than about 2 or 3 volts for this MOSFET, it will start conducting current from between pins 3 and 2. It's reverse biased. So then now this node right here by R8 is grounded after this control line turns 5 volts from ground. And now that that's 5 volts, this will now become 5 volts, and then there will be a difference between pins 1 and 3 for VGS here. And so I guess let's just say that isn't connected again. Then the 12 volt line would go through this 10K resistor, and then the difference between the gate and the source would just be 0, because you'd be getting 12 volts up here, and then you'd be getting 12 volts through 1. But when you conduct the ground through here, current's going to take the path of least resistance, so then current going to be grounded on this R8 line, and then 12 volts here is just going to go into pin 3 and not also pin 1. So then VGS will compare that difference and say, hey, the source is 12 volts and then the gate is 0. So then VGS is going to be negative 12 volts, which is enough to conduct current between pins 3 and 4. So this is a lot larger of a MOSFET because the lights and the horn draw up to a couple amps each. I think most of our headlights run at half an amp continuous, and then the horn will be about 3.5 amps on startup, and then it'll fall back down to like 1 or 2 amps continuous. But yeah, that's pretty much it. That's kind of the bread and butter of our circuit. It's just a basic MOSFET buffer with an NMOS and a PMOS, and they are spec'd high enough so that they can output at least like up to like 5 or 10 amps. It's way over spec'd now. And so the reason for that is because when we first designed this board last year, we did not think about how much current the horn or the lights would draw. So most of these MOSFETs are very standard SOT23 MOSFETs, and these are still okay to use when you're just powering stuff off the microcontroller, because you don't want the microcontroller or like it's not going to draw much current directly through this, because you're buffering that voltage so that whatever it's pulling through Q3 is going to get drawn through our 12 volt line going into the board through power board, which could be either 12 volt main or 12 volt crit depending on if it's Bps Strobe or not. Instead of getting pulled through this microcontroller that's only going to want to output like 50 milliamps at most or something like that. So that's kind of why we have that. But for the horn, before we were way under spec'd on it, and then it would just start to melt. And so with this board, we pretty much added a lot of redundancies, a lot of overspecking. So just in case we needed to change anything in our system last minute, the board was built for that. And so this actually had a really interesting application at race, because our horn broke because we were using it so much when we were passing people on the track. And so we had to go run to the shop and get a new horn, and we didn't know how much current it was going to draw. But this spec handled up to 10 amps instead of only 2 or 3 like it uses. So we were able to swap a new one in just like that and not worry about it. And so this entire circuit is the exact same thing for the turn signals left and right, the strobe control, which is our Bps strobe, and our brake control. And it's also the same for our center brake control on the rear of the car. And then we have a spare circuit called spare B. This is just in case we add another light strip somewhere or another implementation that wasn't planned initially during the development phase. And then same with the horn. So then the way that that outputs from the circuit, I guess, is, what we do is after that output here, we have this 12 volt line that now is turned on with the headlight. And then we go over to the fuse and connector output portion. So now this headlight goes from 0 volts to 12 volts. And so it's fused, and it also has a test point, like I mentioned in the button board video. So most of these fuses, it has them set for 1 amp. We could update those for, it might be more for the horn. We might have not put it on here, but the fuse is spec'd for that much on the board. We soldered it. So similar to like we have on our power circuit, like I mentioned in the button board video, we have a 12.4 volt TVS diode that'll break down after 12 volts. At this point, it'd be 12.4 volts. So that if there's ever a jump in that output voltage, since this is directly coming from power board and it isn't getting through that power circuit in 5 volts, we want to have a TVS diode here. If there's a voltage spike, it will immediately shunt down to ground instead of going out the board and damaging either our horn or our light systems. So you can see that each of these go to the connector, and so you'll notice that it's a 6-pin connector, and then there's 3 12 volt outputs per connector, and then there's 3 ground connections. And so this is just so that you can basically complete the circuit on HAL. Before, we had only one 6-pin connector, and it had all like 12 volt outputs instead of with the ground, and so we had to get the ground connection from somewhere else in the electrical system. This way, it's a lot easier to complete the circuit, know where everything's going, and it's a plug in and play thing of where we don't have to trace around wires. And so that was another thing I made a point to do, because through that design phase and through debugging the car, we learned, hey, this was really annoying, and we wanted to fix it. And so we fixed it, and it was a lot easier on race this year. So seeing that continuous development and design from one summer to the next year of work was really interesting, especially after doing just like the board design for a year. So it's the same thing here with the turn signals, pretty much just the exact same connector setup, copy and paste. And that's most of the circuit. Like I said, this whole buffer circuit was kind of the main thing. Just a lot of small continuous improvements from what we've built on. Our goal is we don't want to have to completely change everything every year and find new issues. We want to work on the issues that we fix right away and make consistent and steady solutions to them the next design year, so that we just continuously improve our car and our electrical system while not doing as much work. So on here, I think we'll have both boards. Yes. So here's kind of an example of the board we did to fix the horn issue when it broke. So this happened right when we implemented this board about a summer ago, when we first put the board in. And so what happened was, basically, we had to add in this giant MOSFET because these MOSFETs right here were not equipped to handle 3 amps of current. We smelled it and it bubbled when we tried to turn the horn on. So this was an old version of the board. This is what we had for race 1 year. And then after managing and developing the board with a couple new members this year, this is what we got. So it's a little larger now, but you can see that it's a lot more over-spec'd. You can see it takes up a lot more room with the larger connectors, more connectors, the fuses, and then the larger MOSFETs for each of the circuit. So this is kind of interesting because you only see the top part here. I'll hide this. So there's a whole nother circuit on the back that handles the rest of that MOSFET buffer. And so you also notice that this is a 4-layer board instead of a 2-layer board like we had before. This was a choice that I made just so it would make life a little easier on the designers, and it would also teach them kind of what to think about with a 4-layer board. You'll also notice that most of these current inputs are a lot larger. That's just because we're dealing with a lot more current in general. So I just beefed up a lot of the traces there just in case. But that whole power circuit is kind of the same. Similar like what I did in power board, I recommended just doing a straight column of it so you knew that everything around here was related to the power circuit. We have our software on the next part of the board. Similar to before, the CAN lines go into the same place like in button board. We have the filtering capacitors, which are 10 picofarads, which are very small, and then the terminating resistor, which we don't actually use on the board, but we kept the pads just to make it easy. One thing with the CAN line that I didn't mention in the last video is we like to keep them very close, because if you split them up, things will get very noisy, and then they might not communicate well between each other, and then you might start to lose packets or not able to send them out of the board. So another thing, I guess really with this circuit is you can see the test points, you can see like how large the traces are. A default trace in Altium is 10 mils. I use 70. You can do a trace width calculator to find, based on the length of it and the width of it, how much current it can output. This is pretty over-spec'd. Any of these traces this wide should be able to output at least like 5 amps, probably more anyways. But we only use it up to 3 normally, but we wanted to over-spec things. We have all our fuses right here on the top. We have our big MOSFETs, and then on the bottom we have the rest of that MOSFET buffer circuit, which just involves different resistors and that NMOS that went with the microcontroller control line that you can see right here. So all of these pieces except for like Q3, the FDD4141 part, are on the bottom. And a lot of that work was kind of started on by our new members, and I was kind of just helping out, showing, hey, maybe this would be a good idea, or if they were lost or they didn't know how to do something in Altium, I would kind of guide them towards it. But I tried to kind of let them figure things out on their own and then just provide advice and let them get the hands-on experience like I learned last year. But yeah, so we kind of planned that out together, and I kind of watched them implement a lot of these choices and things that we discussed. So it was really fun. This video kind of goes in a pair with the button board one. So if you have any more questions, or maybe it seemed like I skipped over something, feel free to go over that video and watch it. It's a little longer since I just kind of started with a lot more stuff in general. I'm still planning on recording a video for the head node and BPS changes I did. If you also want any further questions or answers, feel free to leave a comment. Otherwise, you can go to my website and I'll have a little write-up talking about this stuff too. I'm also going to try and include documentation somewhere, since we have write-ups on what these boards do on a more technical level, on different scopes of like a system level, a board level, maybe like how does it interact with this thing or the other boards or software. So yeah, I'll try and include those somewhere too. But that's all I got for now. Thank you so much for watching. I'll probably post more in the future, but I'm just trying to crank through these technical videos so I can get them posted on my stuff somewhere. But yeah, thank you. Have a good day.